In this video, we will be going over some operational amplifier problems found in previous quizzes. The first quiz we will be going over is 2018. Here is the circuit. Let's take a look at Part A, finding the transfer function and the cutoff frequency. The first thing to note about this circuit is that it's inverting, which means the transfer function Vout over Vin will be equal to negative ZF divided by Zi. We want to simplify the circuit components so that we have equivalent impedances. For Zi, we see a resistor and capacitor in series. This means Zi is equal to R1 plus 1 over j omega C1. For Zf, we only see a capacitor, so Zf is equal to 1 over j omega C2. Putting the transfer function equal to negative Zf over Zi, we get negative 1 divided by j omega C2 divided by R1 plus 1 over j omega C1. Remember, we want to put the equation into standard form for a first-order circuit in order to find the cutoff frequency. To do so, multiply it by j omega C1 to the numerator and the denominator. This simplifies to negative C1 divided by C2 times 1 over 1 plus j omega R1 C1. We can then see that the cutoff frequency is 1 divided by R1 C1. We can also see that this is a low-pass filter by noting that as j omega goes to infinity, the transfer function goes to 0. For Part B, we need to determine the input impedance at the Vn node. The inverting input will try to follow the non-inverting input, which in this case is ground. The input voltage, being driven by the non-inverting input, can then be said to be virtually the same as ground, which is 0. This is the voltage input seen by the amplifier over the input impedance. Due to this virtual ground, the input impedance, Zn, is equal to the impedance to the inverting input, Zi, that we found previously as a series combination of R1 plus 1 over j omega C1. For Part C, the output impedance at the Vout node only depends on the voltage input, not the current output. Since the voltage input is 0, the output impedance is equal to 0. Let's look at 2019 now. Here's the circuit. As you can see, it's a current in, voltage out circuit. Let's look at finding the transfer function. Again, the circuit is an inverting op-amp with a virtual ground at the inverting input. Using KCL at the Vin node, we can see that In equals a negative Vout divided by Zf, which rearranges to Vout divided by In equals a negative Zf. Since the circuit is current in, voltage out, the transfer function is equal to Vout divided by In. We can again simplify Zf to the parallel combination of the resistor and the inductor. This yields Rj omega L divided by R plus j omega L. Now plug this into the equation above. To get the standard form, divide by R for negative j omega L divided by 1 plus j omega L over R. From this equation, we can find the cutoff frequency to be R divided by L. As j omega goes to infinity, the circuit reaches its max amplitude, so the circuit is therefore a high-pass filter. For Part B, we want the input impedance at the In node. Since the inverting input Vn is a virtual ground, it is equal to 0 independent of In. Therefore, the input impedance is 0. For C, we want to find the output impedance at the Vout node. The Vout, in this case, is also independent of Iout, and the output impedance is thus 0. Go ahead and try 2020 on your own. Keep in mind what a virtual ground may do to any parallel circuit elements. Check your answer using the solutions page from the website. You've got this.